In this part of the Computational Intelligence course related to fuzzy systems, we continue with fuzzy controllers. Remember that the rule evaluation results in a fuzzy set for the output, which should be defuzzified for obtaining crisp values as the controller output. We will consider the most common defuzzification methods, which are Max Criterion, mean of maxima, center of gravity, and center of area. Up to now, we considered the mapping between each input tuple and the corresponding output. The output is description of an output value as fuzzy set. Defuzzification interface derives crisp value from the fuzzy output. This step is called defuzzification. The most common methods are Max Criterion, mean of maxima, center of gravity, and also a variation of it called center of area. In the Max Criterion method, we choose an arbitrary y value from the reference set for which the membership value of the output reaches the maximum membership value. If we consider this fuzzy set for the output, we choose an arbitrary y value in this region. So any value here can be chosen. The advantages are it can be applied for any arbitrary fuzzy sets and it is applicable for any domain Y. The disadvantages are which value of the maximum membership is to be used. Any value here can be used. Because of that, it may be a value chosen arbitrarily, so random values, and thus it results in non-deterministic controller. This leads to discontinuous control actions. The second method for the defuzzification is mean of maxima, shortly MOM. We have these preconditions. Y is interval and Y max is defined as the Y values such that for any Y prime in the same reference set, the output value obtained from the rule for Y prime should be less than the output value determined by the rule at point Y should satisfy. And this should be non-empty and measurable. And furthermore, also, Y max is the set of Y values in the reference set such that the membership value obtained as a result of considering the rules is maximal. And if these conditions are satisfied, then we are going to calculate a crisp output value, which is the mean value of the Y maximum. So if we consider, for example, this membership function for the output, here in this interval, the value of the membership is maximum. So we are considering this interval and we are trying to find out where is the mean of the maximum. If we have finite number of Y values, if it is finite, then we sum up all Y values for which the membership value is maximum, and we divide the summation, the result of the summation, by the number of elements considered here. So in this way, we find out what is the mean of the maxima. If we have continuous values, in that case, we find out what is the integral of Y dy. Here, Y is element of the region for which the membership value is maximum, divided by dy integral calculated for the same region. Another approach is center of gravity, shortly COG. Same preconditions as mean of maximum method is used. Here, as the crisp value, we are trying to find out the center of gravity divided by area of membership output. And if y is finite, again, we are considering y value is multiplied by the membership output for each y value. Here we are not considering only the y values for which the membership is maximum. Instead of that, we are considering all the y values. So yi is multiplied by the membership value, and then we are dividing it with the summation of the membership values for each possible yi. This is for the discrete case, and for continuous case, we have to consider the integral of the y multiplied by the membership value, and this integral is calculated over all y values on the reference set, and we divide it by the integral of the membership values on the same region. Here we have y multiplied by the membership. Here we consider only membership value. The advantages are nearly always smooth behavior. A certain rule does not dominate. We are considering all the rules. We are calculating the integral in all this region. And here all the rules are considered. So a certain rule does not dominate. The disadvantages are there is no semantic justification, the computation is long, and counterintuitive results are possible. Instead of center of gravity, center of area method may be used. In that case, we take a value such that it splits the membership output into two parts having equal areas. So if this is the membership function for the output, this is calculated as a result of the rules, and we are trying to find a point such that the area in the left and the area in the right are the same. It is required to compute the center of gravity and also mean of maximum of fuzzy sets shown below. And these calculations are to be done based on finite set where y is 0, 1 up to 10, this discrete points, and also the infinite set, the interval between 0 and 10. So this is requiring continuous calculation, and for this one we are going to apply the discrete calculation. Now we are going to find out the center of gravity for the continuous and discrete output space. For the continuous output space, because our reference set has value between 0 and 10, we have to consider integral from 0 to 10, the value of y here multiplied by the membership value of the output. So we have y multiplied by the membership value for the output and dy, and it is divided by the integral from 0 to 10, again the same interval. We are finding the integral of the membership values over y. For the membership value here, we have three different regions. For this region, from 0 to 5, the membership value is 0.4. and then from 5 to 7, we write the line equation for this line. Again, we multiply with y dy, and here y dy. And for the last part from 7 to 10, the value is 0.8 y dy we have here. And for the denominator, here we have, as the result of the integral, here we have from 0 to 5, the length is 5, multiplied by 0.4. Here we have an area such that we have a trapezoid. So to find out the area of this trapezoid, we add the value here, which is 0.8, and the value here is 0.4. We add them up, divide by 2, and this is multiplied by 2, which is the length of the region. So this is the area of trapezoid here. And for the last region from 7 to 10, the length is 3, the value is 0.8. So it is the area of this region. The denominator is the area here. The integral for the numerator, when calculated, it is approximately equal to 38.7, and this denominator is 5.6, and the result is 0.9 approximately. That means that here we have the center of gravity calculated for the continuous case. And if we are going to find what is the center of gravity, if only discrete values are constant here at the points 0, 1 up to 10, if it was a discrete output space instead of this continuous space, then for y values, here we are taking the summation 0, 1, 2, 3, 4 up to 5, we are multiplying with 0.4, and for the second part we have 0.6 multiplied by 6, the value here is 0.6 multiplied by 6, and for this part at 7, 8, 9, and 10, the value is 0.8, we are multiplying with y, and then we are summing them up. And for the denominator, we have here 6 values, and for all of them, the value is 0.4, and here for this part, only for one value, the output is 0.6, and here for 4 different values, the output is 0.8. We add them up. So the denominator is equal to 36.8, denominator 6.2, and we find out the output, crisp output calculated as the center of gravity for the discrete case 5.9. So here at this point is the center of gravity for the discrete case. However, if we are going to find out what is the mean of maximum for the continuous case from 7 to 10, the membership value for the output is maximum. So we are considering this region from 7 to 10 y dy, and also from 7 to 10 we are considering dy. And if this is calculated y dy. This integral is y squared divided by 2, and it is calculated at endpoint 10 and 7. So we have 50 minus 24.5. And for dy, the integral is equal to y. It is evaluated at 10 and minus 7. So this is 3. The result is 8.5. So the mean of maximum is 7.5 for the continuous case. And if we are going to consider the discrete case, in that case we have to consider 7, 8, 9, and 10. These y values are added, and we have 4 different values used here. So it is divided by 4. So this is 34 divided by 4. We obtain 8.5. This is again the mean of maximum for the discrete case. Here there is an example such that here as the membership function we have such a fuzzy set, and here if we find out mean of maximum, we have 2 points here, and mean of the maximum is corresponding to 0.0. And also, if we consider center of gravity, we have a triangle here and also the same triangle here. If we find out what is the center of gravity, again we will find out 0. But if you consider this membership functions, we have a center of gravity of or mean of maximum as the value of y is at a point such that the membership for the output is 0. So this is not a desirable case. We would prefer to have a high membership value for the point that we are going to apply to control the environment.